Welcome to A Million Miles Beyond Midnight. I'm Bill Higgins. My day job, I'm a physicist at Fermilab, the particle accelerator lab near Chicago. But in my spare time, I volunteer for NASA because I love spaceflight, I love astronomy, and a lot of related matters. And I volunteered for a program where people are asked to bring information about NASA and its missions and other scientific ideas to the public. In fact, that's probably the subject of my second slide. The first thing I want to say is that the Hubble, or the James Webb Space Telescope, my subject today, is a very large and complicated project, and I find that to make a short talk, I may have had to skip over your favorite aspect of the Webb telescope. So please forgive me, and if I've left out something that you particularly liked. As a solar system ambassador, I've gotten briefings from scientists associated with the telescope, and I've been allowed to borrow a whole bunch of slides or PowerPoint presentations from various people. So the scientists on this list: John Mather, Gerald Chris, Margaret Meixner, Alex Fullerton, and Jason Tillmanson have contributed some slides to my presentation. This is a great picture here, a photograph of a mock-up of the spacecraft, where you can see the shiny gold array of hexagons on top, which is the business end of the telescope. That's the optical apparatus, and a bunch of grayish, which are in this picture, but really a multi-layer silvery thing that's very large, way bigger than the people, underneath the telescope. That is the sun shield, and underneath, where you can't see, there would be a spacecraft bus. And there are a lot of institutions like Goddard Space Flight Center, the Space Telescope Science Institute in Baltimore, and Johns Hopkins University that are involved in running this project. I've taken the last slide in my presentation and put it here at the beginning because it involves it will answer questions that you probably have, like, when is this spacecraft going to be launched, and how's it doing? And the answer is that the very, very complicated project is near the end of its road. That the telescope part was mated to the spacecraft part about a year ago in August of 2019. They did the final tests on the sun shield, on unfolding and deploying the sun shield in later in 2019. This year they've been doing a whole lot of testing, including something called the comprehensive system test, with shaking out lots of the electrical systems and the signals. And they announced another delay of the launch date in July, August. The ground system test, where the folks at the control center in Baltimore tried to operate that spacecraft in California and run it through an entire beginning, middle, end sequence of scientific science observation operations. And it's waiting. They're still doing various tests, but it will be shipped reasonably soon over the sea and through the Panama Canal from California to South America, to the Kourou launch site in French Guiana, where the European Space Agency will launch it on Halloween of next year. Telescopes in space. You're familiar with the Hubble Space Telescope, and probably with others. The Hubble being the most famous of all space telescopes at this point in history, and it's good to think about the Hubble to begin to understand the Webb. Hubble was launched 30 years ago in 1990. and it's orbiting in low Earth orbit, and it's got a 2.8 meter mirror, an 8-foot mirror, 96 inch if you like. Hubble can see the colors that you can see, visible light, and it goes a little. It also can reach a little way into the infrared, and that's very scientifically useful, and a little way into the ultraviolet, which has its own uses. The Hubble was deployed by the space shuttle, by astronauts on the space shuttle, and astronauts returned to it 5 times for servicing to upgrade, replace instruments, repair things, upgrade computers, solar panels, and so forth. All very famous. The Webb telescope is named the Webb telescope, the James Webb Space Telescope, because of James E. Webb. Projects like this are often named after a scientist, like a famous astronomer or something. And this one is named after a manager, the second administrator of NASA, who bossed NASA through much of the Apollo project, sending people to the moon, but also played a big role in making sure that NASA had a serious space science program, or a group of science programs. And under his administration, NASA began proposal efforts for large space telescopes in the 1960s, which didn't really come to fruition until the Hubble was launched in 1990. But he's as the father of those things. It's nice to recognize that the people who manage projects contribute a whole lot as well as the scientists. So James Webb is honored here. Here's a slide that has sort of the basic facts, or the high-level summary. The Webb will be a telescope much bigger in its light gathering area than the Hubble. Rather than 2.8 meters in diameter, it's got a mirror that's approximately 6.5 meters in diameter. It's really made up of many smaller segments, 18-segment mirror. It works in the infrared, and it is designed to operate at quite a low temperature, like 40 degrees Kelvin, or I don't know, that's probably more than a couple hundred degrees below 0 centigrade. Right? And the instruments were all designed for the best performance in the infrared. As I said, it will launch next year, according to schedule, on an Ariane 5 rocket supplied by the European Space Agency, and it will go to the Sun-Earth L2 point, which I will explain in due time. It's planned for a nominal 5-year science mission, but the goal is really to keep operating it for at least 10 years if everything is working. But people always are always conservative in specifying these kinds of mission durations. The folks that are running it, well, it's a cooperation between the American Space Agency, NASA, the European Space Agency, and the Canadian Space Agency, the Canadian Space Agency. And the Goddard Space Flight Center, a NASA center, is the lead in managing the project. It's collaborating with these other organizational groups, and the company that's building, or has built Webb, is the Northrop Grumman, and it will be operated as the Hubble is by the Space Telescope Science Institute on the campus of Johns Hopkins University in Baltimore. So they have been operating Hubble for 30 years. They know how to plan observations and deal with a group of users and so forth. You want to know more about this? There's a site called JWST, James Webb Space Telescope.nasa.gov, and you can learn much more. The cost of the project is $8.8 billion in cash. It's estimated, but that does not count the launch, which is worth a few $100 million more by the European Space Agency. I don't really have that number, but it's a nice, it's a very, it's ESA's in-kind contribution to the project. Here we are with Hubble compared to Webb. You can see that Webb is a larger spacecraft as well as a considerably larger mirror. Here's pictures of the mirrors side by side. It not only has a bigger a diameter mirror, but we can, what really counts here in the telescope performance is the area of the mirror, and it has over 6 times the area of Hubble's mirror. That's important for how much light it can gather and how much detail it can resolve in celestial objects. Here's a picture of the mirror made out, as I said, of 18 segments. The mirrors are metal hexagons. They're made of beryllium. Let's see. And beryllium is light and strong and rigid, and at the cold temperatures this thing will operate at. And the mirror segments are given a thin coating of gold, which looks kind of yellowish at wavelengths we can see, but is a nice, pretty much uniform, high quality reflector at the infrared wavelengths that Webb mostly cares about. And here's a nice plot that's a little puzzling at a glance, but it shows you on the top the spectrum of light, where the parts that we can see are indicated in colors we can see, like blue and green and yellow. Okay, so wavelengths of a few tenths of a micrometer or a few tenths of a micron are here. Red is sort of 0.7 microns. Okay, so the near infrared beyond what we could see is 0.8 microns, about 1 micron, 2 microns, and so forth. And Hubble, and this box gives you an idea of the light collecting area, more or less, of Hubble, combined with the wavelength in this direction. You can see that Hubble can detect stuff down out to maybe a couple of microns, and it works nicely in the infrared. But Webb can't see very far into the visible, like it could see red, but it can't see, its instruments are not sensitive to, green or blue light. But it has a much longer range than Hubble in wavelengths on this plot, and it has a much larger collecting area. So the amount of light it can gather and the range of different kinds of light is quite good. Down here we have a sister of Hubble called the Spitzer telescope, which an excellent infrared space telescope that operated for many years, and it had a smaller mirror but a much longer reach into the infrared than either Hubble or Webb. So this works out to Webb is 100 times more sensitive than Hubble in the work that it can do with the light coming in, and the design requirement was 10 times the image sharpness, or in astronomer talk, the angular resolution of Hubble in the infrared light. And various instruments aboard Webb allow the study of the incoming light out to 27 microns, which is way long infrared compared to what I could see. Quick word on infrared light. It is these are wavelengths longer, as I was saying, than the wavelengths we can see, and different materials have different optical properties. So infrared light can actually pass through some materials that visible light cannot pass through, and indeed vice versa in some cases. So here is a person with a plastic bag photographed in visible light, and the dark plastic garbage bag is opaque, and you can't see anything that's inside the bag. But in infrared, the kind of infrared light that's emitted by warm objects, heat, giving off heat, passes right through this thing. So the infrared camera can see this guy's hand. You can see that his skin is glowing more brightly and more yellowishly than his cooler clothing. Can't see through his glasses at all because although they're transparent in visible wavelengths, they're completely opaque in this set of infrared wavelengths we're using. And basically, I would say, as a physicist, I would say infrared light, an infrared telescope can access a different set of physical phenomena than visible light. The light that comes to us from the cosmos comes from various processes, right? Warm things are glowing. Atomic transitions are happening from excited states. There's some laser action. There's some molecules wiggling, and all of this stuff, all the different physical processes give off light at various wavelengths, and combining what an infrared telescope can see with information from what a visible light telescope can see, and maybe a radio telescope, and maybe an ultraviolet telescope, can give astronomers a much better picture of what's going on inside a star, a galaxy, a molecular cloud, or the whole universe than they could see if they only had one telescope. Here's a postcard you may be familiar with, a particularly spectacular observation that Hubble made, looking deep into a tiny area of the sky and finding that if you stare at it long enough, there is light from a whole heck of a lot of galaxies, large and small, near and far, well, mostly far, available. And this distant kind of stuff is what Webb was built to probe. And one more thing about looking at galaxies far away is that there's a property of light that if something is moving away from you, the light that it emits is redder than if you happen to be standing right next to it without moving. The phenomenon called the red shift. And if a thing is moving toward you, light shifts to be somewhat bluer. As it moves away, the wavelengths, the waves coming that you could see going, the wavelengths of the photons, of the light coming at your eye, are stretched out by this receding velocity, and approaching things, things moving towards you would have light that's squashed together because of that speed. This is the so-called Doppler shift, or the famous red shift, because mostly a lot of interesting things in astronomy are moving away from us rather than towards us. But all of this is governed by mathematics that introduces a scale factor called z, and the redshift z. And sometimes you will hear astronomers talk about a z of 1 or a z of 3 or whatever, and that's what they're talking about. It turns out, as Mr. Hubble found out, that objects which are further away from us on a cosmic scale tend to be moving away from us at an increasing speed. That the further away something is, the larger the speed is, and we can't directly measure how far away a distant galaxy is in most cases, but we can measure its wavelength, and by information in its wavelength, we can get distances. And that's how we've built up a picture of cosmology over the years. Here's a picture of sketching out what we know about cosmology from the moment of the Big Bang going forward in time to the left here, to the modern universe. You are here, living in one of many galaxies that populate the universe with a lot of empty space between them. Once upon a time, the universe was very hot and very dense, and the process by which we change from this universe to this universe is really interesting, and you want to be able to probe it at all wavelengths. Well, and Hubble has done a great job, and other telescopes have done a great job at exploring these events. Naturally, events that happen in the early universe are very far away from us because the light from them is just getting to us now a few billion years later, right? The obvious problem is that these things are very faint because these are very far away. So there's a limit to the faintest things that your telescope can see. And if you had a somewhat bigger telescope, you could see even fainter things. So that's one reason for building Webb as a larger telescope than Hubble. And because this stuff is also moving away from us faster than the stuff that we have previously observed, we expect that the light from it is much redder, and lots of information has shifted into infrared light, and that's the reason, or that's a primary reason why Webb has been built to be very good in middle and far infrared wavelengths. It should be able to look, we hope, at the first galaxies, and even further back, perhaps to the era when the first stars began to condense out of the remains of the Big Bang and to turn on. Before that, there was a so-called dark age when the stars hadn't formed yet, so we don't get any light from that age, and we don't have we don't have useful information there. Webb carries four major science instruments contributed by various institutions in various countries, and each one of these is a large, complicated project with a whole lot of collaborators, and that has required years of testing. With a big mirror and a big spacecraft need instruments that can exploit its capabilities fully, and so these are extremely sophisticated gadgets, and I'll just touch on them briefly. But the top one is the NIRCam, the near infrared camera of the University of Arizona, is it does imaging, although you will see pictures from it, but it is also able to get some spectrographic information about the different wavelengths, a spectrum is very precious to astrophysicists, and it can do some spectroscopy, but there's even better spectroscopy coming out of the near infrared spectrograph, an IR spec here, near spec, I guess it's called, and that's contributed by the European Space Agency. So in the near infrared, the shorter wavelengths of say a few microns that Webb can see, these two instruments will be working, and they will cover that part of the spectrum. There's an instrument called the mid-infrared that goes on to 10 microns, 20 microns, out to 27 microns of wavelengths, and that so much deeper into the infrared, and that will tell us about phenomena like very, very low temperature, the heat coming from very low temperature things in the cosmos, and it will do as well imaging and spectroscopy, you can get, and there will be more spectroscopy from the near infrared imaging slitless spectrograph contributed by the Canadian Space Agency, and they also part of this is also the fine guidance sensor, which is a thing for helping to point the telescope precisely. There are four. Now, if you have a space telescope, and it's brand new and it's bigger than previous space telescopes, you could look at anything you want, and there's all kinds of information you can get about your favorite astronomical phenomenon. But there are science goals for Webb kind of organized into into four themes. So looking at those faint objects from the first era when light began to return to the universe is at the end of the Dark Ages. Is one set of studies figuring out how stars get born, and you don't have to look at the early universe for this. It's nice to look at how the first stars were born, but stars are getting born all the time. They're getting born today, so you could view stars, the evolution of stars, at all kinds of stages if you have the right instruments. And as stars are born, we have been learning planetary systems are also often born with a star, and that's a field of study that's really been blossoming in recent decades. The stars and other material after the Big Bang turned into large assemblies of like hundreds of millions or billions of solar masses. And so how galaxies came together, how galaxies are born and sorted themselves out in the history of the cosmos is another theme. And finally, planetary systems. You can look at planets. You can look at things in the solar system, especially in the cold parts at the edge. You can look at planetary. You can look at protoplanets and circumstellar disks that are starting to form planets in other systems. And of course, everybody is interested in exoplanets. I think I might.
Bill, you have about 20 minutes left.
Yeah, I think I might rush through the thumbnail science here, but some of I have slides that illustrate some of the points I was taking. At the beginning of the universe, the Big Bang is pretty smooth. It's an almost uniform distribution of material and energy, and as it cools down, gravity causes little irregularities in the Big Bang distribution of material to draw in and attract each other. And because that's happening, there are also voids being created, and so we begin to get sort of a filament structure to the universe, and those filaments gradually turn as we get denser and denser places. Finally, are the birthplace of galaxies. Trying to observe something about that process is a nice goal for Webb. Can we, if it can see much fainter things than, say, Hubble or other telescopes could see in space, then could it see perhaps even the earliest galaxies? There's hope for that, and studies planned for that. They using the instruments listed here. There are very faint, very red distant galaxies in this picture, and they've been marked with red circles. We'll skip that. I already talked a bit about the assembly of galaxies without telling you anything about how it's done. Likewise, I won't say much about how stars are born. There's a standard how stars are born slide here that one often sees in astronomy talks. There is another famous Hubble picture, the Eagle Nebula, which dramatizes like a diagram really doesn't do, that there's something awesome going on in outer space, clouds that are of material that are condensing into stars and perhaps planets, and other there are places where there are not materials in between these clouds and fingers that are there because nearby stars have ionized have kind of blown away the gas and dust from this area. There's a whole process of this, and you really want to study it. And you can study it in more or less invisible light, as Hubble did, but it's also possible to point a telescope like maybe Spitzer at it and look at the same thing in infrared light. And we look at more at visible and infrared, and visible and infrared. The clouds that were opaque in visible light are more transparent in infrared, and not not as obscured. And so we can sort of see inside the fingers. You can see stars and molecular clouds that are giving off infrared light from within these, or you can see objects behind the fingers. So that is the kind of thing that you might expect to do if you were studying protoplanet or studying star evolution in with Webb. The planetary science community also needs to also gets its share of attention from Webb, and we'll be doing we'll be doing studies. Yeah, as I say, disks of dust circling other stars give us a glimpse into the formation of solar systems. We're all interested in habitable zones where much science fiction takes place, and NIRCam it will be used for studying other solar systems, and it will also be looking at dust and comets and moons and Kuiper belt objects, the frozen icy balls in our outer solar system. And the hot discipline of exoplanet science is just waiting for a bigger space telescope that gives people more detail. Hubble has given a tiny taste of the very, very difficult measurement of trying to see some features of an atmosphere of a planet that's circling another star and crossing across the face of its star. Webb, well, this is such a hard measurement that even Webb won't increase our supply of exoplanet atmospheres very much. It will be able to do a lot more than Hubble, and as being more hugely sensitive, it will be able to do a lot with faint, small, subtle changes in the light, which is where the details of an atmosphere are hiding. I note that there's also an interesting field of exoplanet studies where people look at the reflected light that a planet is giving off, and that it stops giving off as it passes behind its star. So if it passes in front of the star, we get a shadow, and that's how measuring the dip of light from the shadow is something that has been a fruitful source of exoplanet information. But we can also watch the planet disappear behind the star if we can take the large amount of light the star is pointing out and notice that it's disappeared. That amount of light has gone down just a little in some sensitive measurement, and comes back when the star emerges behind. And that kind of information tells you how much light the planet is reflecting. I will skip over the solar system science, and in fact, I have showed you the 4 instruments, and the technical specs on wavelengths and angular resolution are in here, and I'm going to replace that with simply the statement that each instrument is a box filled with fiendishly clever optical wizardry, and each one is worth a long briefing. Just to stand in for all of its sisters, I'm going to show you the guts of NIRCam, the near infrared camera, where light is coming in from the focal plane of the telescope mirror here, and getting reflected, bounced around, passed through filters, perhaps run across gratings and such to split into a long wavelength portion, which is where there's an instrument that's good at long wavelengths here, and an instrument that's good at short wavelengths here, and thoroughly dissected by as I say, fiendishly clever mechanisms. I'll also mention the mid-infrared instrument MIRI is not satisfied with running at the normal temperature of all the other instruments, but it's actually actively cooled by a cryogenic gadget, a two-stage mechanical cooler down to 7 degrees Kelvin, or I guess 7 Kelvin properly. Webb is, as I said, much more sensitive than Hubble. It can see if you're looking for a faint object and you point the telescope at your faint object for a long time, it could see something the size of a bumblebee at the distance of the moon, energies in what astronomers call the nanojansky level. And if you were looking for bright objects, and short exposures, and maybe taking a bunch of exposures to get a lot done, a lot of targets looked at in a short time, it is good for. It's got some systems to optimize for doing a lot with a brief exposure of light, or looking at just part of the or grouping detectors together to read them faster, and it can observe everything in the solar system from Mars outwards, and should be able to give us spectrograms from the transits of exoplanet stars.
About
just
10,
a picture. Yeah, 10.
10. And we have questions also.
Okay. A Hubble galaxy looks like this. We expect that in this simulation, a Webb will be able to see somewhat more detail in an object like this. And here's the spacecraft. Want to tell me the question?
We have a question in the question window and also the chat window. I can read them off if you like.
Yeah, go ahead.
Okay, question from Chris Mullen. Is Webb expected to see the first or second generation of stars formed, and how much redshift are they expected to have?
I didn't memorize the answer to that question. I think they have some confidence for the sort of second generation of stars after an earliest stars have died, and they're talking like they have considerable hope of the earliest generation of stars. But I gather that that's a hard measurement. Sorry, I'm not as well versed in that. Yeah.
And our second question is from Brandy Brock. Does science understand where the Earth is located in the universe, like in center, middle, or edge?
The universe doesn't really have a center. It just goes on and on as far as we know. So there is no special center to it. But we do understand where the Earth is, and what nearby stuff looks like and what distant stuff looks like out to sort of billions of light years from here. And we have a good handle on what the Big Bang looked like that we came from, and there's this middle period where it's dark and we don't have a good idea. But yeah, I would say all in all, we have a good idea of the situation of the Earth in the universe. Let me charge on because I have not showed you much about the spacecraft, and here it is. The telescope has this big primary mirror I've been talking about, a support structure that supports the secondary mirror, and the light is bounced from the primary mirror, focused past, it goes to the secondary mirror, and the secondary mirror reflects it through a hole in the center of the primary mirror to a box in the back here where the integrated science module, where all the instruments live. The telescope needs to be cold, and it needs to look so it needs to be shaded from the sun, and there is an elaborate 5-layer silvery sun shield, much bigger than the telescope structure itself, underneath it here. So the sun is on this side, and the spacecraft will be operated so that the hot side always faces the sun and the cold side always faces away from the sun. And beyond this, in the sort of on the warm side, there is a spacecraft bus, which is has the computers and propulsion and communication solar power and so forth, that normal stuff that you'd expect a spacecraft to carry. And all of this very, very large structure has to be folded up and so that it fits neatly inside an Ariane 5 rocket. And this is kind of what it looks like when it's stowed. Here's the spacecraft in its glory from the point of view of the primary mirror here. You can see a black structure in the center that's part of the apparatus that the light goes into and gets conveyed to the instruments on the back, and the spacecraft bus down here, and a little communication dish. It's actually a pretty big communication dish, but it's a big spacecraft. Here we see the hot side, and you can see a little more detail of the spacecraft and kind of the rails that have to extend out in order to unfold the sun shield after launch. And there's a solar array right here.
We have about 5 minutes left.
And okay, I will skip over details of optical design because I just said that in plain language. I will say where this goes. These spacecraft will be launched to orbit the sun, just as the Earth does. So it won't be strictly speaking, in Earth orbit. It will go out to a 1.5 million kilometers beyond the Earth at the so-called L2 point, the L2 Lagrange point, where it's possible to make a semi-stable orbit, and it will always be further away from the sun than the Earth does. And in fact, it will always be in the sky at midnight. If you look up, it will be in your sky somewhere, because it will always be over the dark side of the Earth, but 1 million miles away from it. Hence that's why it's called the talk, 1 million miles beyond midnight. And I just said that. Yeah, the spacecraft because it always has to point away from the sun, cannot see the whole universe at any time. There's only a certain part of the cosmos that it's able to look at. But over the course of the year, as it orbits around the sun, new parts of the cosmos will become into its field of view. So if you schedule your observation right, you'll always be able to look at almost anything. You can't look at Venus or Earth or Mercury with this thing. There are no plans to service this telescope after its launch, and remembering all the astronaut trips to Hubble, that makes a lot of people nervous. So I've thrown in this graphic that shows all the space telescopes that Richard Cruz chose to draw in history. All of them fairly successful. Only 3 of these had attention from astronauts that were involved in their repair or servicing somehow. All of these other guys were designed to work without anybody repairing them and distant from any people, and they all delivered just fine. So spacecraft engineers do know how to do this. It's demanding. You need to test everything very carefully, but the Webb people are confident that they can make this thing work. They have tested over and over again. After launch, here's how the mission will go. A few minutes within hours after lunch, I guess a half an hour after lunch, they will deploy the solar array, and then they'll test the communications, and then the sun shield and the telescope mirrors and so forth will start to fold over the next couple of weeks, and it will finally arrive at L2 a couple weeks later and begin a commissioning phase where they calibrate the instruments and test that they're working properly and so forth. And then the scientists will begin to do their observations, and the Space Telescope Science Institute will coordinate all of that. Here's a photograph of it. We're close to out of time, I imagine, but here's what it looked like in the hangar last August, when it was, or August before last, when it was being mated. The telescope part was being connected to the spacecraft part. Lots of people riding, people in bunny suits riding lifts and checking on all the pieces of this. October tests of the sun shield. You can see the shiny silver sheets of the sun shield in all its glory. Oh yes, and here is Randall Munroe's joke about all of the many years over which this telescope has been planned, and all of the many launch dates that people have thought it might have been gradually increasing with time, and so he's hoping that someday this will cross over with the real calendar, which goes one day per day. Since this cartoon was published, the launch date has moved again, partly because of COVID-19 slowdowns, from March of 2021 to October of 2021. But we'll still probably launch before Randall Munroe's date if we are all fortunate. So stay tuned for news about the Webb telescope, and after it gets launched and operational, stay tuned for a lot of interesting scientific work, maybe including discoveries of stuff we have no idea about yet. Thank you.